Okay, here we go. Elastic and inelastic collisions. So this goes back to when we were talking about conservation of linear motion. All momentum is conserved. Okay? And it's conserved in all collisions. So either we can have an elastic collision or an inelastic collision. And so elastic collisions happen when total kinetic energy is conserved. So then obviously inelastic is when total kinetic energy is not conserved. And all that means at that point is that that energy is being transferred into something else. What would it be transferred into? If you think of an inelastic collision.
One vehicle hitting another one.
Yeah, but what would be, where would you have the loss of kinetic energy? Transferring to?
Like the other vehicle.
Sound energy, right? Heat energy, light energy, okay? It's also bent here. It's also due to bending, crumpling, breaking, any deformation, changing your state. But it's also sound and heat. All collisions at a macroscopic meaning large scale. So what you can see with the naked eye, all collisions at a macroscopic level are inelastic. But there was sound energy there, right?
Yeah.
So it wasn't total kinetic energy.
Otherwise it would have came all the way back up.
Exactly. Conservation of energy applies to inelastic collisions because it's only the kinetic energy is not conserved. Conservation of energy is still maintained. It's that transfer of energy. So while kinetic energy, what you have before will equal to what you have after, you have a conversion of that energy. Okay? Momentum's always conserved though. So let's look at an argon atom. When we're talking about atoms, are we talking macroscopic or microscopic? Microscopic. So are we talking inelastic or elastic? Elastic. Okay? An argon atom with a mass of 6.63 times 10 to the negative 26 kilograms travels at 17 meters per second, right? And strikes another identical argon atom dead center traveling at 20 meters per second left. The first atom rebounds at 20 meters per second while the second atom moves at 17 meters per second right. Determine if the collision is elastic. So we're going to be looking at kinetic energy. What the heck? EK before is going to be equal to EK prime. So before and after. And how do we find kinetic energy? Dig deep in the recesses of your brain. Or use your data sheet. 1/2 mv squared. Okay, 1/2 mv squared for the first argon atom, and 1/2 mv squared for the second argon is going to equal prime. I'm going to put a little tick up here just to show you that it's prime. Okay, because it's elastic, we have conservation before and after. So, we can simplify this before we start doing any kind of math work. We know that we have the mass, it's a mass of argon striking another mass of argon. There is only one mass for argon. Okay? So we can pull out the 1.5 before, and you're left with V1 squared plus V2 squared is equal to and these are the after velocities. Okay, are you understanding that part of how I'm able to pull out the half and the mass?
Yeah.
Jaden's a yes, anybody else a yes? Okay. Okay, so it's asking us, the first atom rebounds, determine if the collision is elastic. So, we're looking at, because these are the same, they cancel out. So we're left with v1 squared plus v2 squared is equal to v1 2 plus v1 v2 squared, but after. Okay. So the first one, argon atom with a mass of 6.63 travels 17 meters per second, right? And strikes another identical argon atom dead center, traveling 20 meters per second to the left. And how do we indicate left? The negative. However, at the end of the day, we're squaring it. Okay? The first atom rebounds at 20. Left, so negative, plus 17 meters per second squared to the right. Now, when we're looking at these numbers before we crack out our calculator, 20 squared plus 17 squared is going to equal 17 squared plus 20 squared. So when we could still go through the motions and we could still do the math. Okay, double check my math. Therefore, it's elastic. Okay.
Whoa.
What do you know?
What do we know?
What
Okay.
do we know?
Are we good so far? Yeah? Okay. Alright. A test used to measure the speed of bullets is to fire a bullet at a block of wood that is hung like a pendulum. Don't let me forget to show you a video. By measuring the maximum vertical height of the block of wood with the bullet lodged in it allows one to calculate the initial speed of the bullet. If a bullet has a mass of 14.9 grams and the block of wood has a mass of 2 kilograms, when the bullet collides with the block of wood, the pendulum swings to a maximum vertical height of 21.9 centimeters. Determine the velocity of the bullet just before impact with the block of wood. Come on in. Oh, hi.
Well,
Thank
Mr.
you.
Fire.
It's Miss Pryor, because Miss Pryor left her wallet at home. Thank you.
Yeah,
You're
but,
going down.
we'll do because we forgot lots of stuff.
Okay, you're good. I'm recording, so
Okay.
bye. Determine the velocity of the bullet just before impact with the block of wood. Okay? So let's start with writing down some information, because there's a lot of words here and we need to extract out what we have and what we don't have. So what do we have?
We have a mass of...
Mass of what, Jaden?
14.9
What is that?
grams.
But the mass of what?
The bullet.
The bullet is equal to 14.9 grams.
She was asking.
Okay, Cameron, is there another piece of information?
The wood has a mass of 2 kilograms.
Okay. I'm going to put a W for wood is 2.00 kilograms. Another piece of information, Sophia? And any more information, Chris?
It probably is. You're looking for the velocity of the bullet.
Okay. Now, there's a couple things we need to do before we move on that are really easy.
Oh, it has to be meters.
Has to be meters. So how do we do that, Chris?
You divide by 100.
So divide by 100, and we get
2.1 or 0.2 Yeah.
Okay. And what about the mass? Reese, you said something? Or somebody said something about the mass?
It's gotta be in the kilograms.
So how do we do that?
5,000.
So we get
I like that.
okay, 0.0149 kilograms. Okay. So the first thing that we need to do, there's a couple of steps we have to do here. The first thing we have to do is use conservation of energy. To find the speed, because we have too many unknowns. Okay, once we have velocity on the after section, then what are we going to do? Do you think? How do we find velocity? We've already used conservation of energy here. What's another way that we find velocity? It's the title of our unit. Momentum. We're going to use the conservation of momentum. Okay? Okay, so number 1 says use conservation of energy to find speed of the block and bullet after the collision. So we have mass before, we have height, we need a velocity. So what are we going to be looking at? When the bullet, this sentence right here, when the bullet collides with the block of wood, the pendulum swings to a maximum vertical height of 21.9 centimeters. What do we know with height when we're talking conservation of energy?
Is gravity?
Has potential
Oh, that's
energy. Okay? That's bottom. Okay? So the block of them together. So this one here, we have potential energy. And it needs to be equal to, once we have potential energy and it hits that maximum height, we then have what? We go from potential energy to kinetic energy. Okay. So we are looking for which component, did we say, in number 1? The velocity.
The speed, I guess.
Right. So we have 2 times mgh divided by m, and all square rooted equals velocity. And this cancels out inside. The masses cancel each other out.
So it's 2G.
Yep, 2gh. So what do we get for a value here?
Is it 2.07?
It is 2.07.
Good.
So the velocity of the wood and the block after the collision is 2.07. So then we go and we're like, okay, I found that. What is it that exactly we're looking at? We're looking at a bullet traveling this way into a block of wood. This is our before. In our after, we have a block of wood and the bullet is inside of it. Okay? Do we understand that from the instructions?
Yep.
Alright, so this one here has a mass equals 0.0149 and the velocity is unknown. This one has a mass of 2 kilograms and a velocity of 0. How'd you get that, Chris?
The bullet hasn't hit it yet and it's not moving.
Exactly. Okay, so afterwards we have a mass of
2.0149.
because they're combined together, and we have a velocity of 2.07 meters per second. So here we have momentum equals m1 v1. Here we have momentum equals 2 times 0. And here momentum prime is equal to 2.0149 times 2.07. So we have 0.10149 times v1 plus 0 is equal to, what's 2.0149 times 2.07? And you're keeping your decimals throughout this whole part. Sophie, if you move like 2 inches either side, you would be like out of Cameron's thing and you'd be out of the way of the video. Or you could keep leaning to the side, depending how Cameron moves her body. What do we get for P prime?
4.176620885.
Okay. So we have 0.0149 times V1 is equal to 4.1766. So V1 is equal to
Is it 280.3?
Yep, but give me in significant digits.
Oh boy. 280, I guess.
280
Yeah.
meters per second. And it's asking for velocity. So what else do we... Direction.
To right. Or
To the right.
the block.
Positive.
Towards the block. Forward. Those all work. Whatever is our positive words, positive direction words. So right, towards,
The word
forward,
positive.
same direction. Okay? Alright. Makes sense? It's recalling a lot of knowledge, though, isn't it?
That one wasn't too bad.
No. Alright, what principles were used to calculate the velocity of the bullet? We wrote them out.
potential energy equal to kinetic
Hold
energy.
up, you never showed us the video. Conservation of energy.
Oh, yeah.
Conservation of momentum. Okay.
Okay. As an aside note, this is what we call principle number 5 in physics. And we call this principle number 4. I haven't seen a need for you to know, like on the test, what is principle number 4? I have never seen that, but this just is an aside. So is the collision elastic or inelastic? How do we figure that out? If it's elastic or inelastic, we're looking at the conservation of
Energy.
and that is the, how do we find it? Which kind of energy? Kinetic energy. Okay, the EK before versus the EK prime. So before, what do we have? We have the bullet and the block, and afterwards we have the block with the bullet inside. So this one would be 1/2 mv squared. Okay? So what's common between all three of those? Right. What's common?
Math.
Why, Chris? Say it again.
The one on the right hand goes with block and
They're two different masses, right? There's the mass of the bullet and the mass of the block.
I thought we were just looking at the equation.
Well, we are.
Yeah.
The what, Reese? What's common?
What?
The 1/2. Okay. So we're just going to go 0.0149 times by our velocity before was 280. We calculated that out. Whoops, we don't need the 1/2. And we calculated the speed to be 2.0728 squared. So we have, what's 280 squared times 0.0149? What'd you get, Cameron?
1,168.
Oops, kilograms, meters squared, seconds squared. And then this one was 0. I meant 2.0149 times 2.0728 squared. Did you get a number, Sophia? Jaden?
No.
8.657. 658, I guess, rounded.
As an aside, what is this unit? What do we call that guy?
Oh, is that like newtons or something?
No, newtons is kilograms meters per second squared.
Oh.
Right? Newtons is force times mass times
Yeah.
acceleration. Energy is measured in,
Watts.
that's power.
Joules.
joules.
Uh,
Okay. So, does 1168 equal 8.657? So that's your question. No, it doesn't equal it. So then it's inelastic. Did this collision happen on a microscopic level or a macroscopic level?
Macro.
Macro. We could see it. You could see the bullet hit the block, right?
Oh,
So
I mean,
it's macroscopic.
yeah, it's not like you can trace the bullet with your eye.
Yeah, but the point is you can see it. Okay? So I'm going to give you guys, there's some practice problems. There's 5. They're theory questions. So I will give you, let's say 15 minutes. And then I'll show you the video and then you can have the rest of the time for a work
I
block.
want to see the video first.
Yeah, I wanted, that's what I was gonna ask. Have you seen the video first?
Nope.
Shucks.